In the previous lesson, we used compare instruction and timer to design a 1000 cyclic control and a sequence. However, for some complex sequence cyclic controls, using general basic logic instructions can easily cause confusion in the control program's thinking and make the program more complex. Therefore, we introduced the sequence control design method. Sequence control is also known as step-by-step control. According to the idea of sequence control, the execution of the program is divided into various program steps based on the production process. Each program step consists of 3 parts: entry conditions, program processing, and transition conditions. The bit of the common bit memory M represents the state steps of the sequence control program. When we use sequence control design method, firstly, based on the process flow diagram of the system, draw a sequence function diagram, and then design a ladder diagram according to the sequence function diagram. The design of sequence stop control for 3 electric motors. This is a process flow diagram. Create a sequence function diagram based on the process flow diagram. Prepare to use the double line box M0.0 to represent the initial step M0.0, and use the initialization pulse M1.0 to enter the initial step M0.0, where M0.0 equals 1 as the active step. Separate each step with conversion conditions. Press the start button SB1, which corresponds to I0.0 being connected, indicating that the transition condition is met and the transition is made to the next process 1. Process 1 corresponds to step 1 M0.1, at which point M0.0 is reset to 0, initial step M0.0 is an inactive step, and M0.1 is set to 1, converting step 1 M0.1 to an active step. Starting motor 1 corresponds to the Q0.1 output in step 1 M0.1, and the action or output corresponding to each step represents the processing of the program for that step. Press the start button SB2, which corresponds to I0.1 being connected, indicating that the transition condition is met and the transition is made to the next process 2. Process 2 corresponds to step 2 M0.2. At this point, M0.1 is reset to 0, step M0.1 is inactive, and M0.2 is set to 1. Step 2 M0.2 becomes active. Starting motor 2 corresponds to the Q0.2 output in step 2 M0.2. Press the start button SB3, which corresponds to I0.2 being connected, indicating that the transition condition is met and the transition is made to the next process 3. Process 3 corresponds to step 3 M0.3. At this point, M0.2 is reset to 0, step 2 M0.2 is inactive, and M0.3 is set to 1. Step 3 M0.3 is converted to an active step. Start motor 3, corresponding to Q0.3 output in step 3 M0.3. Press the stop button SB0 to activate I0.3, indicating that the conversion condition is met and the transition is ready. Prepare the corresponding initial step M0.0. At this point, M0.3 is reset to 0, step 3 M0.3 is inactive, and M0.0 is set to 1. The initial step M0.0 becomes active. The M bit in the box equals 1, indicating that this step is an active step. The M bit in the box is 0, indicating that this step is inactive. Only in the active step will the corresponding action or output be executed. Actions or outputs corresponding to other inactive steps will not be executed. When the active step is completed and the conversion condition is met, the current active step is closed and the transition to the next step becomes active. The sequence function diagram is converted into a ladder diagram, and in the properties of the hardware device PLC, start the system memory ND1. When the PLC goes from stop to run, using initialization pulse M1.0, a scanning cycle is turned on, and the reset domain instruction is executed to reset M0.0, M0.1, M0.2, M0.3, and 4 bits to 0. The execution of the reset domain instruction is Q0.1, Q0.2, Q0.3, with 3 bits reset to 0. Execute the set instruction to set M0.0 equals 1, making the initial step active. As pressing the stop button also requires entering the initial step, and I0.3 is connected in parallel to the M1.0 contact. When M0.0 is connected and pressing the start button, SB1 corresponds to I0.0 being connected, the conversion condition is met. The reset instruction is executed to reset M0.0 to 0, and the initial step is inactive. At the same time, the set instruction is executed to set M0.1 to 1. This step becomes active and M0.1 equals 1. The set instruction is executed to set the output Q0.1 to 1, completing the work of this step. When M0.1 is connected and pressing the start button, S2 corresponds to I0.1 being connected, the conversion condition is met. The reset instruction is executed to reset M0.1 to 0, and the initial step is inactive. At the same time, the set instruction is executed to set M0.2 to 1. This step becomes active and M0.2 equals 1. The set instruction is executed to set the output Q0.2 to 1, completing the work of this step. When M0.2 is connected and the SB3 start button is pressed, corresponding to I0.2 being connected, the conversion condition is met. The reset instruction is executed to reset M0.2 to 0, and the step of turning off M0.2 becomes inactive. At the same time, the set instruction is executed to set M0.3 to 1, and M0.3 becomes active. M0.3 equals 1. The set instruction is executed to set the output Q0.3 to 1, completing the work of this step. 3 motors are all started and running, and the program keeps running cyclically, but only the M0.3 step is executed. At any time, press the stop button SB0 to connect I0.3, execute the reset domain instruction to reset M0.0, M0.1, M0.2, M0.3, and 4 bits to 0, and execute the reset domain instruction to reset Q0.1, Q0.2, Q0.3, and all 3 bits are reset to 0. Execute the set instruction to make M0.0 equal to 1 and enter the initial step. The initial step is active, and all 3 motors stop running. This section learned the design method of single sequence sequential control, and the next section will learn the design method of selecting branch sequence and parallel branch sequence sequential control.